With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
To uncover football tactics, we create spaces and times. We use time query, construct spaces, construct times. Our approach was used for reconstructing team tactics in different classes of game situation. Our domain experts are happy, and the Germans shall win again and again.
MetroSets is an online platform for visualizing sets as metro maps. In this style of drawing, sets are represented with metro lines, while the elements they contain are represented as stations. MetroSets is implemented using a modular 4-step pipeline with a variety of choices for each step. The final visualization is interactive with support for all common set operations. MetroSets is fully implemented and can be found at the displayed URL.
The recent technological advancements in mixed reality extend our ability to evaluate new visualizations faster than ever before. In a user study with 60 participants, we compared 4 situated visualizations using 5 different empirical methods. In contrast to prior work, our results showed no dependency between the user's feedback and the empirical methods.
Atmospheric convection is one of the most important phenomena in meteorology. It is responsible for cloud formation and storms. Yet, the measurements of the convective processes are expensive and scarce. In IsoTrotter, we collaborate with a domain expert to build an empirical model of the atmospheric convection based on paragliding data. We design a novel visual parameter space analysis technique using isostructures in the parameter space to explain and validate the model.
Capturing analytic provenance is important for refining sense-making analysis. However, understanding this provenance can be difficult in distributed collaborations. We present a novel concept, crowd auditing, as a way to help debug distributed sense-making. We implemented the concept in a system called CrowdTrace that visualizes and traces the analysis provenance and elicit feedback to improve the analysis.
We present responsive methods. Hello and good morning or good afternoon, depending on where you are, and welcome to this VIS session on sense and explainabilities. And as you might have guessed from the title of the session, the presentations will be about how to make sense of complex machine learning models using exploratory analysis and different types of explanations. And today we have 6 exciting paper presentations. And the first one is titled OoDAnalyzer, interactive analysis of out-of-distribution samples, which will be presented by Changjian Chen from Tsinghua University. Take it away, please.
Everyone, I'm Changjian Chen from Tsinghua University. Today, I'd like to introduce our work, OoDAnalyzer, interactive analysis of out-of-distribution samples. This is a joint work with Jun, Yafeng, Yang, Han, Songtao, and Shixia. Out-of-distribution samples, or OOD samples, refer to test samples that are not well covered by training data, like these black cats. They are misclassified with high confidence due to their black bodies. The high confidence misclassification of OOD samples can lead to serious incidents, like self-driving car crashes. To tackle the problem of OOD samples, there are 2 challenges. First, we need to detect OOD samples in test data accurately. Second, even if we find the OOD samples, we cannot understand the underlying reasons for the appearance of such OOD samples. Without the understanding, it is difficult to systematically address the problem caused by OOD samples. For OOD detection, many methods have been proposed. However, this method either uses a single algorithm or a few algorithms with high-level features, resulting in limited coverage of feature and algorithms. For explanation, many visualization methods have been developed to analyze anomalies. However, as they are not tailored to OOD samples, they cannot be extended to analyze OOD samples directly. To tackle these 2 problems, we first make a practical improvement of the Ensemble OD detection method by combining more features and algorithms for high coverage. And we also developed a grid-based visualization to analyze OD samples in context. Based on them, we developed OoDAnalyzer to explain why OD samples appear. Next, I will introduce an overview of our system. Given training and test data, both high and low-level features are extracted first. These features are then fed into the Ensemble OD detection method to identify OD samples. Then, grid-based visualization is used to analyze OD samples in context. Series maps are also provided to understand the model prediction. With the help of visualization, the user can identify the reason why OD samples appear. Accordingly, more data is added into training data to retrain the model. Then the experts can start a new round of analysis. Before I explain the technique details, I will introduce the case studies to demonstrate how to use the OoDAnalyzer to analyze OD samples. We conducted 2 case studies, one on an animal dataset and one on a retail edema dataset. In the first case study, we found 5 reasons why samples are out of distribution. In the second case study, we identified 2 reasons. The accuracy of both case studies was improved. Next, I will focus on the first one. OoDAnalyzer contains 3 views: a control panel on the left to help explorations, an information panel on the right to show images and science maps, and a grid-based visualization in the middle to show all the samples in context. In this visualization, each grid represents one sample. The color encodes the category. The lightness encodes the OD score. The higher the OD score, the more likely the samples is to be OD. From the overview, several areas of OD candidates arouse the interest of the experts. The experts decide to analyze them one by one. He starts from region A. Region A mixes dogs and cats together. Zoom in, he finds many misclassified dark-colored cats and light-colored dogs. Then he selects these 2 categories for further exploration. Their science maps highlight their whole body, which means their bodies are important regions for model prediction. It is unusual because the heads of dogs and cats are the keys to make prediction. He then compares the distribution of training and test data side by side. In training data, dogs are mostly in dark colors and cats are mostly in light colors. In test data, however, dogs and cats are in different colors. Thus, the experts confirm that lacking diversity in colors between cats and dogs causes these OD samples. Back to the overview, the experts continues with other regions. In region B, some cartoon images are misclassified as rabbits. He decides to display training and test data together. In this view, circles represent training samples and squares represent the test samples. There are no similar cartoon images in training data around them, but many rabbits with big ears. The series maps also stress the rabbit-like ears. The experts indicate that missing cartoon images accounts for such OD samples. Next, the experts move to region C. In this region, he selects some images and finds many wolves confused with dogs, like this one and this one. By examining their neighbors, he finds some huskies. He turns to the training data, but can hardly see huskies. So he considers lacking huskies is the major reason for the appearance of these OD samples. Similarly, in region D, the experts find some tabby cats misclassified as tigers because of the black stripes on their bodies. Few cats in training data have such patterns. This is identified as an underlying cause to have such OD samples. To handle a problem of OD samples, we add the corresponding missing images to training data and get increases in accuracy. Moreover, after retraining the model, there are fewer OD candidates in the updated layout. After a period of time, new images come into test data and cause accuracy degradation. And other experts want to make a diagnosis and reload data in our system. He quickly recognized 2 regions of high OD scores. Zooming into these regions, he discovers leopards hidden among tigers. As knowing that training data include no leopards, he identifies leopard as a new category. More leopards are added into the training dataset, and the accuracy of the model goes up again. After demonstrating the case study, I want to explain the technique details. First, I will introduce the Ensemble OD Detection method. Previous work, deep ensembles, used the ensemble method to detect OD samples. However, it uses only high-level features with a single classifier, leading to limited model capacity and local optimum. To tackle this problem, we made a practical improvement to this ensemble method. First, to improve the model capacity, we enlarged the feature set by using both high-level and low-level features. Second, to escape the local minimum, we enlarged the algorithm set by varying the hyperparameters of logistical regression. We evaluate our method on 3 datasets, which shows that our method performs best in most cases. Then, we introduce grid-based visualization. To explain why all these samples appear, the experts need to analyze them in the contents of other samples. We first use a scatter plot to visualize samples. Despite the promise of cluster separation and data distribution preservation, it cannot support content-level exploration due to overlap and space wasting. To tackle this, we turn to grid-based visualization, which is shown to be effective at providing a content overview of data. A practical method for generating a grid layout is a two-step way. The data is first projected as 2D scattered points. Then, these points are assigned to grids by solving a linear assignment problem. This problem is like putting these apples to dishes, one for each, such that the total distance to move apples is minimized. However, the time complexity to solve it is cubic, which cannot meet the interactive requirement. To tackle this, we developed a KN-based approximation method for acceleration. The simple idea is to reduce the search space by prohibiting apples from being placed in distant dishes. However, this strategy cannot guarantee that there will be a solution. We thus developed a grid strategy to adjust the edges based on Hall's theorem, which shows that a matching exists if the degree of each vertex equals k. The basic idea of this grid strategy is to remove some edges of apples whose degree is larger than 2, and add some edges of apples whose degree is less than 2, until they all satisfy Hall's theorem. Then we can find the matching. After the adjustment, the linear assignment problem can be solved in n², which can meet an interactive requirement. To conclude our work, we present OoDAnalyzer to interactively identify OD samples and explain them in context. We made a practical improvement to the Ensemble OD Detection method and developed a KN-based grid layout algorithm. In the future, there are several directions to follow. First, we plan to investigate how to select suitable parameters for the OD detection method, as inappropriate settings can lead to poor performance. Second, we plan to extend our system to handle test data. Finally, we may integrate our method with feature engineering or interactive model analysis to further improve model performance. Thanks for your attention. Our codes and demo are available on our project website. I'm happy to take any questions.
So thank you very much, Changjian, for this very interesting talk. And it's very nice to see that your code is available publicly for other researchers to have a look at. Moving on to the questions. So I'm going to have a look at the Discord channel. So waiting for the questions, I probably have a couple myself. So I probably have missed it during the presentation, but I was not very clear how the regions of interest on the visualizations were selected by the experts. Was this done based on the lightness of the color? Have you noticed whether it was kind of drawn, people were drawn to the areas with, is it the darkest color, which implies a higher OD score? Or was it more like open exploration going between different areas?
Thanks for your question. Yes, the darkness stands for the OD score. The more dark of the samples, the higher the OD score is, which means this samples is more likely to be OD.
Okay, so people were going probably towards those regions first, perhaps, to check, I guess.
Yes.
Okay, thank you. Going back to Discord to see if there are more questions. So we have a question. So how do you define the number of rows and columns for your grid visualization?
Thanks for your question. For now, we use 25 multiple 25 grid to display images for show the image context and show as many as an image possible.
Thank you. So I've got another questions on Discord just came up. So do you already have any ideas on feature engineering integration?
For now, we extracted the features, extracted both low-level and high-level features. So for low-level features, we use some classical feature extraction methods. And for high-level features, we use convolutional neural network to extract these features.
Okay, thank you for your answer. We probably have time for one last question. We just have one now on Discord. So many of the features you have mentioned are abstract. How do you tackle cases where the reasons for misclassification are not visually obvious? Very good question.
Thanks for your question. Yes, there are few. We also noticed that there are few samples called unknowns that are not visually obvious, which is we may take into account how to tackle these samples in the future.
Okay, so I think we don't have more time for questions, so let's thank the speaker again. And let's move on to the second talk, which is titled HypoML, Visual Analysis for Hypothesis-Based Evaluation of Machine Learning Models. And the talk will be led by Changjian Wang from Hong Kong University of Science and Technology. I think this is an update from the previously advertised speaker. There was a mistake, and thanks to Chen for making the correction.
Hello, everyone.
So take it away.
Hello everyone, I'm Wang. Today I'm presenting our work, HypoML, Visual Analysis for Hypothesis-Based Evaluation of Machine Learning Models. We can treat machine learning as a type of education, where models learn to make predictions from the training data. Model users and developers may want to understand what concepts has the model learned, as learned concepts are always useful. For example, has the model learned the common orientation of an object? If yes, can the model recognize an object that is rotated from its usual position? Has the model learned the surrounding environment of an object? If yes, will the model fail to recognize an object without its surrounding environment? Testing those concepts is important for us to understand the model behavior so those models can be better deployed to real world. Previous studies has attempted to test those hypotheses from two aspects, black box analysis and white box analysis. Black box analysis treats the ML model as a black box. This analysis can examine how perturbations to model inputs affect the model outputs, and has been supported by many visualization tools. However, it usually supports observations for individual predictions and may not be statistically meaningful. White box analysis, on the contrary, aims to analyze the internal states of ML models. For example, many techniques have been developed to depict what a neuron has learned. However, the depicted patterns provide largely a hunch rather than a solid conclusion. Also, considering the vast number of neurons a network contains, it's impossible to examine all neurons. Therefore, we would like to ask, can we test hypotheses about the model learned concepts in an efficient and statistically meaningful way? To answer this question, we present HypoML, Visual Analysis for Hypothesis-Based Evaluation of Machine Learning Models. The first part of HypoML is a concept-based testing framework. For the input data D, assume we have a concept denoted as plus that is not explicitly defined in input data but is hypothesized to be related to the model prediction. We combine D with plus and D with random noise separately. Using the same training process, the two pairs of datasets generate two ML models. Testing the two models using the two pairs of datasets, we obtain four sets of testing results. Although ML testing typically features many uncontrollable variables, simply compare the average value may not lead to solid conclusions. Statistical comparison between testing results is therefore needed for meaningful analysis. Pairwise comparison among the four sets of results can lead to 6 analyses, which help us test a series of hypotheses about the testing concept. We predefine a set of commonly used hypotheses and formulate the logical inference rules. Those hypotheses include the effect of the testing concept, as well as the bytext of the proposed testing framework. For more details about the predefined hypothesis, please refer to our paper. The hypothesis reasoning can be time-consuming and error-prone, especially considering that the validation of one hypothesis may depend on other hypotheses. For example, this biparty graph summarizes the workflow of the proposed testing framework and demonstrates the complicated logical reasoning. The clustered links provide no clear structures and are difficult to check by eyes. Therefore, an effective visual interface is needed. We reverse the order of the workflow and present it in a top-down manner, which enables users to check the conclusions at first, and then decide whether to check back to the statistical comparison and experiment results for detailed reasoning. Then, we present elements in the workflow using more intuitive visual encodings. The font color of a hypothesis indicates whether it is supported, rejected, or unproven. The relationship between the hypothesis and the statistic comparison is represented using a matrix-based design. The glyphs in each cell indicates whether the analysis in row rejects, supports, unprovens, is conditional on, or is unrelated to the hypothesis in the column. P-value is represented by a glyph to aid memory recall. This glyph is similar to the illustration used for explaining hypothesis testing. The larger the blue area is, the higher the possibility that the difference is not caused by randomness. The p-value is also double encoded using the type of links. A solid link indicates significant difference, while a dotted link indicates insignificant difference. The glyph is used to present the meaning of each set of testing results. The X position of the circle indicates the average value of the results, where the line indicates the results uncertainty. Here, we present two use cases for image classification tasks using convolutional neural networks. More cases are provided in the paper and the supplementary materials. Note that the cases here are not intended to establish the truth of a particular ML technique, but to demonstrate the practical use of HypoML for one model. The first testing concept is rotation regularization. Rotation regularization is used as a data pre-processing in fashion-MNIST datasets. While it is widely accepted that, in theory, convolutional neural network is rotation invariant, it is sometimes unclear whether a specific model has learned these concepts adequately. To test the hypothesis about rotation regularization, we design the experiment as below. We generate data samples by combining several images into one. The original data D are randomly rotated objects, and the plus part is objects in the normal orientations. Using the same training process, we generate two models. Using the two pairs of datasets and the two already trained models, HypoML automatically completes the concept-based testing. Here are the results of the hypothesis testing. All pairwise comparisons are significant, and each hypothesis is either supported or rejected. I will skip details and just jump to the most important conclusion. That is, knowing the common orientation of an object will help the prediction of this model. In other words, this model itself hadn't learned the concept, rotation regularization adequated. The second use case is about color space. While many datasets in computer vision using the RGB color, there is still an unsettled debate about how well the color space influences the model predictions. Here, we show a simple case considering two common color spaces, RGB and HSV. The experiment design is shown here. RGB image is the original data D. HSV image is the actual data containing the testing concept. Instead of directly combining D with the plus part in the input data, which is what we do in the first use case, In this use case, we consider first process this information and then merge them inside the model. We tried different options to merge the two types of information, including merge them using different functions, max and add, and merge them at different positions of the neural network, after the first max pooling layer or after the second max pooling layer. Interestingly, while the results show that the information from another color space HSV may contribute to the model prediction, the results also show that how to merge influence our hypothesis about the usefulness of the HSV space. The testing results change if we merge at different positions or merge using different methods. To conclude, we present an ML testing framework that combines the traditional statistical hypothesis testing with logical reasoning. We develop a visual analysis tool for rapid observation of the conclusions and the logic flow between the testing results and the hypothesis. Meanwhile, we recognize that HypoML is just one of the many steps towards a powerful testing suite for ML models. It has several limitations. For example, extra computation cost for model training and testing is required in this framework. More importantly, there is a need for further inference about subgroup, multimodal, and multi-concept analysis of the testing results. That's all. Thanks for listening. Your questions and comments are welcome.
Hi, thank you very much, Qianwen, for this very interesting talk. And moving on now to the Q&A section.
Hello.
So while waiting for the questions to show up on Discord channel, I have one question myself. So can you tell us a little bit more about how you came up with this set of 12 hypotheses, machine learning hypotheses, and were they validated, for example, with machine learning developers? Can you, for example, add more hypotheses?
Oh, sorry. Yeah. So basically, the ideas come from the fact that we find people conducted a different types of evaluation to like evaluate machine learning models and understanding like what it has learned before they can really apply to real world applications. But the thing that like usually machine learning model contains like a large number of uncontrollable variables, like, and you know, the testing result you get each time might be variance, and sometimes it's not easy to get a statistic conclusion about like whether a model is better than another, and more importantly, like what model has learned. Like for example, sometimes we think the model developers think one feature might be important, but he's not sure like whether the model has really learned it from the training data. And another problem is that sometimes a model learned a feature from the training data, for example, but this feature might be a bias, which is not good for the model prediction. Just like Changjian's presentation, the model learned that might use the color to detect whether it's a cat or a dog, but this is actually a bias and is not a useful feature for the model.
Thank you for the answer. Let's see if you have more questions on Discord. Please post them there if you have any questions. Let's give them a couple of seconds. Otherwise, I have also another general question, which is, can your HypoML tool work with other types of data sets? Sorry, with other types of models?
Yes, actually, it's a model agnostic testing framework, and it can be used to different types of machine learning models. Yeah.
Okay, that's great. Thank you very much. Let's just have a look if there's no questions. No, thank you very much. And great. Let's move on to the next talk. So from CNN, so convolution networks to random forests. And our next talk is titled Explainable Matrix, Visualization for Global and Local Interpretability of Random Forest Classification Ensembles. And the talk will be presented by Mário Popolin Neto.
Hello everyone, my name is Mário Popolin Neto and I'm going to present the paper Explainable Matrix, Visualization for Global and Local Interpretability of Random Forest Classification Ensembles, which I and Fernando Paulovich are the authors. I am a professor at Federal Institute of São Paulo and a PhD candidate from ICMC at the University of São Paulo, both institutions in Brazil. Fernando Paulovich is a professor from Faculty of Computer Science at Dalhousie University, Canada. My presentation will follow this agenda. I will talk about motivation, our solution workflow, and usage scenario, discussion and limitations, and finally, conclusions and future work. Now, let's start by our motivation. Let's imagine a classification model that predicts positive for breast cancer for a particular patient. You might want to know why positive. The doctor could want to investigate the reasons for this outcome or the changes in the patient's records that might result negative. For these issues, model interpretability is the answer. Random forest is one of the most popular classification techniques, but it's a very complex entity for visualization, since it's composed by multiple decision trees. In this context, we propose X-matrix, a novel method for random forest interpretability. Our solution is based on logic rules presented in a matrix visual metaphor, where rules are rows, features are columns, and rules predicates are cells. The X-matrix has a well-defined workflow, which consists of two main steps. The first step is named as vector rules extraction. From a random forest model, a logic rule is extracted from each decision path on every tree. So, taking this random forest as example, for the iris dataset, here we have one decision tree and one decision path. The rule is extracted as a vector, using the decision path boundaries. The predicates are represented by rectangular shapes, followed by class. As example, for this rule to be true, the instance value for sepal length must be between 6.15 and 7.9 and among 0.75 and 1.75 for petal width. Two properties are extracted for each rule, named as coverage and certainty. Higher the coverage, more generic is the rule, while certainty are classes probability. The second step on the workflow is visual explanations. Once the complete set of logic rules is obtained from the extraction process, visual explanations can be built by four guide functions. F1 and F2 defines the rules and features of interest. F3 defines the rules and features ordering by different criteria, and F4 defines a cell icon from rules predicates. These four functions combined result on meaningful visual representations with different purposes. Global for model overview, and local for expecting an instance classification. Okay, once finished the workflow, I will present the X-matrix global and local explanations, showing one hypothetical user scenario. For this, I have Sylvia, a bank manager, using a random forest model and the X-matrix for loan applications evaluation. The global explanation presents all logic rules from the random forest model, In this way, it shows all the knowledge learned by the model. By expecting this explanation, where rules are ordered by importance, Silva can notice that features, account balance, credit amount, and duration of credit are the most important to the model. She can also observe that feature duration of credit appears to have some ranges and class associations on rules with high coverage, noticing some gaps formed by the rules predicates. The global explanation can also present filtered rules. This one has rules filtered by coverage and certainty, showing the most generic and certain knowledge learned by the random forest model. So Silvia discerns better the gaps on feature duration of credit. Low values appear to be more related to class approved. Higher values appear to be more related to class denied. In this way, from the point of view of the most generic and certain knowledge learned by the model, loan applications with lower duration tended to be approved, whereas with higher duration tended to be denied. The local explanation showing used rules presents the logic rules used to classify a particular instance. So it displays the knowledge used in the classification process. In this explanation, instance feature values are represented by dotted lines. So back to our hypothetical usage scenario, Silvia analyzes this explanation, which is for a client that had his loan request denied by the random forest model with 65%. She noticed that only denied rules use the feature length of current employment, being strongly related to the random forest outcome. So she kindly explains to the client that one of the reasons for the denied loan is that he is not long enough in his current job. The local explanation showing smallest changes presents the logic rules that require the minimal change on instance features values, flipping the prediction on the decision trees. So it displays the delta changes on instance features values that may turn the random forest outcome for the instance under analysis. For this local explanation, green represents positive delta changes, whereas purple represents the negative ones. By expecting this local explanation for the client, Silva noticed that negative changes on duration of credit and on credit amount turn through rules of class approved. So, as an alternative, she proposed to the client to decrease values for duration of credit and credit amount, arguing that these updates might turn the loan request to approved. So the client accepts and Silvia decreases values for duration of credit and credit amount. The random forest outcome turns to approved with 57%, and the client gets the loan, as presented by this new local explanation showing the used rules. More examples of applications are found on the paper, including using different datasets. Now about discussion and limitations. The matrix visual metaphor employed on X matrix is more scalable and concise than node link diagrams, since it's capable to present several decision trees and features are ordered in a tabular format. Node link diagrams is a well-recognized metaphor to present nodes and connections. However, the object of analysis on decision trees are the decision paths, and the logic rules enable the analytical tasks presented on the usage scenario. As limitations, scalability can be an issue for global explanations, regarding the total number of rules. For this matter, the solution adopted was to implement rules filtering. The user study revealed good results for global explanations and local explanations showing used rules. However, the delta changes analysis on local explanations showing smallest changes appear to have certain complexity for non-expert users. Now, ending the presentation with conclusions and future work. With global and local explanations, the X-matrix allow overviews of random forest models and the inspections of the classification results. The X-matrix is implemented as a Python package, but it can be implemented in any coding language following the workflow. Although we have created the X-matrix with random forest in mind, it can be used on decision trees or any other model based on logic rules. As future work, we will investigate new ordering and feature criteria, aggregation approaches, and optimize rule-based models. We wish to thank to the valuable comments and suggestions received from the reviewers, the support received from the qualification program of the Federal Institute of São Paulo, Brazil, and the support of the Natural Science and Engineering Research Council of Canada. At last, but not less important, we wish to thank to all VIS committee and staff. Thank you all, and I'm available for questions.
That's fine. So thank you very much, Mário, for this very interesting talk. Moving on to the questions. So we have already a question on Discord. Let me go back. So it goes like this. Maybe it's regarding the loan approval data set. Where does it come from? Is it synthetic, or is it publicly available?
Yes, yes, it's public available. We are using the German Credit Bank dataset. It's a toy dataset from the DECE machine learning repository.
Okay, thank you for the clarification. We also have a second question. Are these thresholds in logical rules understandable by experts?
Yes, we had for non-experts we have not so good results on the local explanation showing smallest changes. We believe that we got this result because of the users not being experts on random forest process of classifying a new instance regarding the voting process of the rules.
Thank you. Another question, and people are actually having lots of comments on the Discord and saying it's very nice work. Can you say something about the scalability of this method? And for example, how many trees or rules can you handle?
Yes, yeah. The scalability can be a problem for global explanations because as we grow the number of trees, we have a lot of rules, right? So we had this kind of problem in global explanations, and we addressed this by filtering the rules and sometimes the features. But about local explanations, when we show a local explanation, we show just one rule per tree. So we don't have a lot of problems with scalability on local explanations.
Thank you. The next question. So do you have an intuition on how many rules can be filtered in the global explanation while maintaining acceptable faithfulness to the original reference model? And it continues like this. For example, have you made any explicit efforts in finding the sweet spot between simplicity and accuracy?
Yes, that depends on the problem that we are working. For example, these explanations for the German credit bank, we have some rules with high coverage and high certainty. So in this way, we can filter these rules by these properties and get a feeling of the most generic and certain knowledge that the learner force model has learned. But sometimes we can get data sets when it's not possible to get rules with high coverage and high certainty. So this can be a problem. But it's also is a limitation of the random forest model for certain kind of problems.
Well, thank you very much. And let's thank Mário again for this great presentation. There are many more questions on Discord, so I encourage you to go and have a look and engage in the discussion.
Okay.
So from matrix visual explanations to the next talk, which uses a different type of explanations, counterfactual explanations in particular. The title of the paper is DECE, Decision Explorer with Counterfactual Explanations for Machine Learning Models. And the presenter is Cheng from Hong Kong University of Science and Technology.
Hi everyone, I'm Cheng. Today I will present the novel work, DECE, Decision Explorer with Counterfactual Explanations for Machine Learning Models. The authors of this work are all from HQSD. Machine learning models are increasingly adapted to make decisions in high-stakes application scenarios, such as healthcare, credit assessments, and job or school admissions. However, the black box nature of some machine learning models brings practical issues. Data subjects or customers may receive undesired predictions from the model and raise a question like, why my request gets rejected? Decision makers such as doctors or policymakers may find the model's prediction untrusted because the prediction does not agree with their prior knowledge. For model developers, the lack of interpretability and transparency makes it hard to detect the model's potential flaws and biases. To address these issues, we introduce counterfactual explanations, a set of model-agnostic explanation techniques. I've introduced the concept of counterfactual explanations through an example. A person submitting a loan request but got rejected by the model. He may wonder why this loan request gets rejected. Explanation is given as, if you earn $500 more each month, your request will be approved. Such an explanation is called a counterfactual explanation. A counterfactual explanation tells the closest possible world to answer a why problem. It describes the smallest change made to the data that alters the prediction result. From the intuition of data scientists, the counterfactual explanations also show how data instance can be altered to cross a model's decision boundaries. Two sets of properties make counterfactual explanations distinguished from existing techniques. First, counterfactual explanations are human-friendly and actionable. No prior knowledge of machine learning is required for users to understand the explanation, and users can take the suggestions to gain the desired result in the future. So counterfactual explanations are good tools to help layman users, such as data subjects, to understand the model. Besides, counterfactual explanations provide grounds in the model's predictions, which are always faithful, and they are good props to explore the model's decision boundaries. These two properties indicate that counterfactual explanations have high potential to be used as a general tool to help advanced users, such as model developers or decision makers, to understand and diagnose models. Some existing works build a visualization system to support counterfactual-based analysis on machine learning models, such as a what-if tool made by Wexler supports counterfactual reasoning to prop classifiers. Another work, Gambit, by Huamin also offers similar functionality for regression models. Both of these two works are designed for model developers and practitioners to analyze the model's prediction on a single instance. In our work, we support general users like data subjects to understand the model and gain suggestions by providing actionable and customizable counterfactual explanations. And we extend the idea of counterfactual-based reasoning to a subgroup level, which helps advanced users gain a higher level understanding of the model. We introduce DECE, Decision Explorer with Counterfactual explanations, which is a visual analytic system that helps users ranging from model developers to data subjects understand and explore a model's decisions on the instance level and the subgroup level. In the instance level, the counterfactual explanations serve as actionable suggestions for data subjects, so it is essential to know what the actionability is. According to a recent work by Matilda, actionable counterfactual explanations should be valid, proximal, and sparse. Besides, by providing diverse options and allowing users to add constraints, it is easier to fit different users' preferences. Then we design a multi-step generation procedure to generate counterfactuals satisfying this criteria. We also design an interface that allows users to query counterfactuals to a single instance with constraints. After clicking the search icon, the top panel will show the prediction result, and the diverse counterfactual explanations as well as the original instance are plotted in the parallel coordinates, where each polyline represents an example. In subgroup level analysis, we aim to help users explore the model's decisions on data subgroup to gain a higher level understanding. We design an exploratory analysis procedure to help users iteratively prep the model. First, users define a subgroup and make a hypothesis on the subgroup's prediction. For example, a hypothesis is like people who are under 30 years old and whose body mass index is under 35 will be predicted healthy by the diabetes predictor. This hypothesis is in the form of an if-then rule. And we generate counterfactual explanations against each instance in this subgroup. One is like this. This counterfactual explanation indicates that the hypothesis is not valid and suggests that users may refine the hypothesis by restricting the conditions. For example, reciting the upper bound of BMI to 32. Such a refinement to the hypothesis is easy to apply when users only consider one or two attributes, but in practice, when users have considered multiple attributes together, the number of refinement options increase exponentially. To deal with the cursor of dimensionality problem, we add constraints to counterfactual explanations. We allow users to focus on one attribute at a time, and we generate counterfactual explanations by only allowing the value of the focused attribute to alter freely, but the value of other attributes should also be within the ranges defined by the subgroup. We call this set of constrained counterfactual explanations as rule support counterfactual examples or R-counterfactuals, which means that these counterfactual examples are used to support or against a rule-based hypothesis. The users can refine the hypothesis by restricting the conditions of the focusing attribute. Now, the hypothesis is valid, which is supported by even potentially unseen examples. Practically, users have to make several rounds of refinement on different attributes to gain a solid conclusion and gain insights into the effect of different attributes on the predictions. Then we introduce a visualization interaction design that supports this exploratory analysis procedure. We first introduce a basic element of our system. This figure shows a visualization of rule support counterfactuals against a target subgroup and a focus constituents feature. We use a histogram to show the distribution of focus features value, and we use another upside-down histogram to show the counterfactuals against it. The color of bars indicates a prediction clause. The color of the right rectangle is assigned to show whether the hypothesis is valid. The deep color indicates that the data with mixed classes can be found, which means that the hypothesis is not valid. And we use a spark line at the bottom to indicate a good split value for users to refine the hypothesis. Users can drag the handles to refine the subgroup. Now we can see the rectangle's color intensity gets lower, which indicates that the hypothesis is closer to a valid one. And the green peak in the spark line also shows that this attribute's range has been refined to a proximal one. To deal with the rest of within subgroup counterfactuals, it is not wise to keep reducing the upper bound of glucose, because very few instances will be included in the new subgroup. Users may check the other attributes. Then we show the full picture of the table view, which supports the subgroup level analysis. Vertically, the table view consists of three parts. From top to bottom, they are the table header, the subgroup list, and the instance length. The table header presents the overall data distribution of the features in a set of linked histograms of bar charts. In a subgroup list, each row represents a subgroup. Users can update, copy, and delete subgroups to maintain a list. When users click a cell in a subgroup list, the instance presents details pertaining to each instance and counterfactual examples. Horizontally, the first column is a prediction column. We use bars to show the number of instances in different classes. The color indicates a prediction class. Each bar we use a solid area to show the number of correctly predicted instances, while a striped area shows the wrongly predicted instances. In feature columns, each column represents a feature. Users can focus on a target subgroup and a target feature by clicking the cell. Then we introduce a case to show how the table wheel works. The other two cases can be found in our paper. In this case, a neural network is trained from Pima Indian diabetes dataset to predict whether the patients will have diabetes in the next 5 years. A medical student wants to know how the model makes predictions for patients under 40 years old. Based on prior knowledge, she formulates a hypothesis that patients under 40 years old whose glucose level is under 100 millimole per liter are likely to be healthy. She first selects a subgroup by limiting the ranges on urge and glucose accordingly. Firstly, she finds that all patients are predicted as negative. However, she also noted that for most of the features, the range box is not transparent, which indicates that the diabetic counterfactual examples can be found within the subgroup, so the hypothesis is not valid. Then she found that the BMI distribution of counterfactuals has saliently shifted to the right. This means that the BMI needs to be increased a lot to make the model more prediction fleet. Thus, she proceeds to refine the subgroup by adding a constraint with BMI under 35 as indicated by the green pig in the bottom sparkline. She also adds a constraint on the DPF feature as for a similar reason and makes the update. After refinement, she found that most of the cells are covered by a transparent range box or filled with mostly light gray bars. The light gray bars indicate that most of the counterfactual examples found by altering this feature are invalid, which is also a sign to show that the hypothesis is closer to a valid one. One exception is the BMI cell, where a few counterfactual examples can still be generated against this subgroup. To check the details, users focus on this subgroup by clicking. After the table header is updated, she filtered the counterfactual examples with BMI under 35 by brushing. Then she found that all valid counterfactual examples have an extremely high pregnancy value, which means patients who have gotten pregnant for many times are exceptions to this hypothesis suggested by the model. So she updated the subgroup with a constraint as pregnancy lower than 6, which covers a majority of the subgroup. After the refinement, she found that the remaining counterfactuals have extremely low blood pressure values, which is very similar with the previous condition. So she updated the lower bound of blood pressure value to 40, which is a normal range. After the third round of refinement, all feature cells are covered with a transparent range box, which means the hypothesis is valid. So now the user is able to draw the conclusion according to this exploration. In conclusion, we present a visual analytic system DECE to support counterfactual-based analysis to machine learning models for different types of users. In the instance level, we support users with actionable and customizable explanations. While in the subgroup level, we support users to make exploratory analysis to gain a higher level understanding of the model. Thanks for listening.
So thank you, Frey, for this very interesting talk. And let's move on to the questions. So I don't see any questions yet on Discord. So if you have any question, please write it on Discord channel for this session. Waiting for that, I have a question myself. So at the end of the counterfactual exploration, especially for the subgroup level, the conclusion that might be reached at the end could be complex, involving a variety of features and constraints. And I was wondering, how easy is it to track the process using which this conclusion was reached? And for example, assuming that you want to reproduce this conclusion.
Thanks for the question. So as you see in the cases, actually the users have to make several rounds of refinements to draw the conclusion. And each refinement, actually one attribute is to a range was set to it. However, so you can see for some features like the number of pregnancy. So actually these features have some specific meaning. So by setting ranges for this feature actually is to exclude some special cases. And in this process, in this refinement, actually the users is able to gain some insight. And you see actually for whether the conclusion includes the patients with pregnancy over 6 or not does not affect the generality of the conclusion a lot, right? So the included instances are very similar. However, I mean, in this process, actually, the users can gain some insights to know what actually the special cases, which is not, I mean, supported by this hypothesis.
Thank you. So we probably have time for one more question. We are probably 5 minutes behind the schedule for this session. So one more question could be a general one. Regarding the generalizability of your methods to other machine learning models and perhaps the size of data sets that can be handled. If you have any comments.
Yeah, thanks for this question. So actually, when we are building this system, one challenge is that currently we did not find any very efficient and scalable generation engine for this counterfactual explanation. So actually, we made our own generation algorithm, which we use mini batch to handle the large data size. So currently, when we are running for around 1,000 instance, or 1 or 2,000 instance, it takes less than 10 seconds for the counterfactual explanation generation for the whole data set. And also we try some larger data set like the HyLog, which contains over 10,000 instances, and it takes about 40 seconds. It's a bit longer. So I think we will in the future works we may use some parallelism algorithms to speed up the generation process.
That's great. Thank you very much. So moving on to the next talk, which the topic of which is class separation and decision boundary analysis. The title of the paper is A Visual Analysis of Class Separations with Locally Linear Segments. And the presenter is Yuxin Ma from Arizona State University.
Hi everyone, I'm Yuxin Ma, currently a postdoc from Vader Lab, Arizona State University. Today I'm going to introduce our work on the visual analysis of class separations with locally linear segments. The concept of labels is a fundamental building block, widely adopted in machine learning tasks, including classification and clustering. To visualize high-dimensional patterns with labels, dimension reduction is an essential approach used to preserve the intrinsic structures in the data, while providing a low-dimensional representation. Two properties are typically considered when applying an algorithm to visualize labeled data instances: linearity and capability of supervision. In linear projections, the data characteristics such as covariance, correlations, input-output relations, and margins between classes can be easily illustrated. However, they lack the ability to extract nonlinear manifolds. The nonlinear methods are able to present nonlinear manifolds in a 2D scatter plot, but the embedded results can be extremely difficult to interpret with distortions. Supervised dimension reduction algorithms tend to increase the similarities of instances in the same class. However, the distortion may increase the uncertainty and errors between instances from different classes and affect the understanding of intra-class relationships, especially when inspecting data distributions near the class separations. To tackle the issue of balancing interpretability and distortion of intrinsic structures, we propose a visual analysis approach that enables the exploration and investigation of complex class separation structures. The core idea of our approach is inspired by the development of locally linear models in classification analysis. The complex class separation is characterized on the basis of locally linear separations, which approximate the original separation, and further supports the visual exploration of how the classes are separated from each other. As described before, the motivation of the approach is to use locally linear separations to approximate the entire discrete boundary, which is similar to local linearity analysis in machine learning, like LIME. Here, we use locally linear segments to represent the set of linear approximations. To extract these segments, we first utilize the power of nonlinear support vector machines to construct a set of Cs near the discrete boundary between classes. By using the support vectors from the support vector machine model as Cs, each support vector is further expanded in the local region to generate a linearly separable set. One issue here is that for those regions where the densities of support vectors, that is to say the Cs, are very high, there may be redundant segments with nearly overlapped separating hyperplanes. So a bottom-up merging procedure is adopted to combine local regions with nearly parallel separating hyperplanes. Finally, after the segments are extracted, we calculate the influence of the extracted segments on the surrounding instances. The data instances that are not Cs are assigned to their nearest segments. Apart from the extraction algorithm, we performed a comprehensive survey of existing works on class separation and discrete boundary analysis in machine learning, topological data analysis, and visualization, and finally distilled a list of analytical tasks for analyzing locally linear segments. The tasks are classified into two main categories: macroscopic analysis for providing an overview of the extracted segments, and microscopic analysis for detailed inspection of selected segments. To provide an overview of the segments as well as their relationships, a segment graph is designed to visualize the relationships in the form of a modified no-link diagram. Here, each circular glyph represents the characteristics of segments, such as the number of covered instances and seeds, and the ratios of instances in each class. The edges between segment glyphs represent whether they are the nearest neighbors of each other. Besides the encoded information on the glyphs, more detailed statistics of segments can be observed in the segment detail view, such as data distributions of covered instances and the dominant features that separate the local regions. At the instance level, we employ linear projection and t-SNE projection of all the data instances to provide an impression of the global data distributions. When a segment glyph is selected in the segment graph, the corresponding covered instances can also be highlighted in the projection results. The last module in the framework is the path exploration view. We designed this view in order to provide a more interactive way of examining the connections between neighboring segments, which are also the neighboring local regions. If two segments are not directly connected, which means they do not share any data instances between each other, an interpolation-based bridging method can help build a smooth path between them. For visualizing the exploration path, we propose a visual design where representative scatter plots for each segment are linked together in a zigzag way. Users can use Turing interactions between any of the two consecutive scatter plots to rotate the linear projection result in order to view how the two segments are connected. We present an example of how to analyze the shuttle stat-log dataset. We choose the three classes in the dataset, Radflow, High, and Bypass, and subsample the number of instances into 400 per class. After the dataset is loaded, we find that the three classes are nearly separated in the initial PCA projection result. However, the boundary between the blue and the orange classes is not linear. In the DECE projection result, the green class is clearly split from the other two classes. In the segment relation view, we discover two communities in the segment graph. The green instances are mainly in community A, while the orange and blue instances lie in community B. The green segments mostly consist of green and orange instances, indicating that the green class is near the orange class but not the blue one. There is an outlying green segment in the community B containing a group of outliers from a larger green cluster. We further investigate how classes are separated and the decisive features that influence the separations in local regions. For the green classes in community A, we check the most important features for each segment. F5, F6, and F7 are the top features, indicating that these features should be considered when separating green instances with others. Next, we explore the main segments between the blue and the orange classes. For the blue and the orange class, we discover two subgroups in community B with different essential features, feature F5 in B1 and feature F7 in B2. We further explore the transition between the two subgroups. The curved edge between segment 2 and 9 indicates an angle between the corresponding separating hyperplanes. In the exploration path, the scatter plot in the middle shows the joint area of two separations where a clear angle transition is depicted. The transition on the path can also be animated by using the slide bar. To summarize our work, we have proposed a novel approach for detecting locally linear separations in high-dimensional label datasets, and a visual analytics framework for exploring complex class boundaries. In the future, we would like to reduce the computational costs on the SVM models, try different seed generation methods, and integrate our approach in diagnosing classification and clustering models. Thanks for your interest, and we're happy to have questions.
So thank you, Yuxin, for this interesting and clear presentation. And moving on to questions, I think we have time for 1 or 2 questions. So we don't have questions at the moment, so waiting for the questions on Discord. So I just have a small question about how do you actually handle the issue of clutter and overplotting on the 2D projections?
Oh, for the 2D projections, basically, I think there are some methods that can be applied to the scatter plots, like the sampling, for some aggregation methods, like if we have some dense clusters, we can use a glyph-like or sampled results to represent such a kind of clusters. So I think that's a broad issue that exists in the scatter plots. So there are some already established methods for handling this issue. Thank you.
That's great. Thank you very much. One final question. I think you mentioned it as part of your future work. Can you just comment a little bit about the scalability of your system, for example, in terms of extraction of local linear segments, runtime, etc., so we have an idea about.
Thank you. So yeah, this is a good question because in our in our algorithm for extracting the local linear segments, we frequently use the support vector machines, linear support vector machines. I saw KPR is asking the same question. So the kernel is linear, and we often use the linear support vector machines to fit the locally linear boundaries in a local region. So this can be a bottleneck when the decision boundary is very complex, because there will be tons of local linear support vector machines to be trained. And speaking of the scalability issue on the interface, so the scatter plot you just mentioned can be one of the problem if the number of instances are very high. And also for the number of extracted segments, that can also be an issue when the number of extracted segments is high. So for these two things, for the scatter plot, we can use the sampling or aggregation methods to reduce the visible elements in the view. And also for the segment graph, we can use filtering methods. We can use some sort of filtering methods to reduce the visible elements. So
great, thank you very much for your answer. And that's all the time we have now for questions for this presentation. Moving on to our final talk, which is titled Visual Analytics Approach for Exploratory Causal Analysis, Exploration, Validation, and Applications. And the speaker is Xiao Shi from Changjian University.
Hi everyone, I'm Xiao from Changjian University. I'm going to introduce our work, a visual analytics approach for exploratory causal analysis, exploration, validation, and applications. Causal reasoning is a common task in data analysis. For example, doctors need to diagnose the disease, marketers hope to understand causes of the revenue, and education analysis would like to understand the factors of admission. Here we use a marketing scenario to better explain the usefulness of causality. Suppose you are a marketer. You assign a task to increase the subscription of users. Usually, you will try to find effective marketing channels to promote the subscription. According to the past records, you may find that email is highly correlated with the subscription. However, the channel selection is still difficult, as you also find that many users receive all the effects from the channels, and it's hard to determine the pure effect of each channel without causality. Given the usefulness of causality, visualization researchers have proposed different methods to facilitate the analysis. A set of works contribute to the empirical studies of visual causality. For example, researchers have tested the efficiency of different visual channels for encoding causalities, and examined the expressiveness of different types of visualizations for presenting the causality. These works provide guidelines for the design of our system. Another set of works focus on designing an interactive system to facilitate the causal analysis. For example, animated glowing polygons are designed to help visually identify causalities in an interactive process. The visual causality analysis is designed to integrate automatic causal discovery algorithms. However, these works focus on a small dataset, which is usually smaller than those in real-world applications. To increase the usability of causal analysis, we designed a system named Causal Explorer. Users can explore the causal graph to perceive the causality and its uncertainty, validate the causality with the raw data, and apply the confirmed causality to what-if analysis. We face two challenges when developing this system. The first challenge is the presentation of large-scale uncertain causalities. When analyzing a high-dimensional dataset, there could be massive compressed causalities, and moreover, the automatic causal discovery raises an uncertainty issue of causalities. How to estimate and present the large-scale uncertain causality remains to be resolved. The second challenge is the implementation of interactive tools for accomplishing what-if analysis. What-if analysis with causalities is an iterative process and is hard to achieve without interactive tools. However, how to integrate human knowledge with causalities for achieving what-if analysis still remains an open research question. Overall, we summarize design needs and implement an interactive system to address the two challenges. We further evaluate the system on two datasets from different domains, and next I will introduce the three parts one by one. First, I will introduce the data structure. Overall, we have three types of data and all of them are categorical data. The first one is observation. It represents variables that we can observe, like patients' profiles and customers' clicking actions. The second one is outcome. It represents variables that can be considered as successive metrics, like the cure rate and the consumption. The last one is intervention. It represents variables that can be directly managed, like the medicine and the promotion channels. On the basis of this structure, we invite 5 data analyses and conduct 2 semi-structured interviews to create their design needs. Finally, we derive 7 design needs across 3 major requirements. The first requirement is the support for examining causal detection results. We need to present large causal graphs since users cannot easily understand the causality of a large dataset. Showing a whole picture can facilitate the understanding. We also need to show the uncertainty of causalities. Causal discovery algorithms usually assign different levels of uncertainty for each causal relation. We need to show this uncertainty to improve the reliability of analysis. Lastly, users need to inspect the data quality since causal discovery usually requires certain assumptions of data, which should be validated with an interface. The second requirement is the support for identifying influential factors. Users need to estimate the influence of different factors on an outcome to help them identify important factors. They also need to see how a factor causally influences an outcome to interpret this influence. The last requirement is the support for making what-if interactions. Users need to simulate plans according to the causality to help them anticipate future situations. They also need to see the comprehensive effect of a what-if interaction to help them prevent side effects. For the causal detection, we first introduce the representation of causality. Causality is usually encoded as a Bayesian network. Each node encodes a variable and each link indicates the causal relation. When there is no edge between two variables, the two variables are independent when controlling other variables. For the causal detection, we first have a score for measuring a causal graph. Given a causal graph and the corresponding data, the score can measure how well the causal graph can be used to fit the data. Bias and information criterion is used for this computation. We use a scalable approach named FGS to detect the causality from large datasets. The detection contains 2 phases. In the forward phase, the method computes a score for each addition of a new edge and add the highest one to the causal graph. This process is iterative and will stop until the score does not increase. The detection then goes to the backward phase. The method computes the score for each deletion of an edge and delete the edge with the highest score. This is also an iterative process which will stop until the score does not increase. According to this detection process, we define the uncertainty of a causal edge as the score difference with and without the edge. We then design an interactive system based on the requirements to analyze and apply the causality. Users can explore the causality with a causal graph view, validate the data and effect with the dimension view, and apply the causality to what-if analysis with the table view. Now let's take a look at the causal graph. We use a pie chart to encode the data distribution of a variable. The edge encodes the causality, and the thickness encodes the uncertainty of causality. We place nodes into layers to ensure that all the causal direction is from up to down to help users more easily perceive the causality. We also use different strategies to increase the scalability of a causal graph. In the initial layer graph, we observe that the chain structure of causality significantly increased the number of layers. We use the strategy of node aggregation to address this problem. Then we can obtain a layout like this with less layers. Another problem is that the causal links overlap with each other even we have used techniques for reducing edge crossings. This is because we have cross-layer links that connect nodes across more than one layer. We use the link reduction strategy and use a glyph to represent the existence of cross-layer links. Finally, we obtain a layout like this. For the what-if analysis, users hover on a row in the table view and a control panel will be shown. Users can click on the intervention button to fix the value of a variable, and the setting of the intervention can be seen in the bottom panel. Users can click the Run button to simulate the intervention, and the effect will be shown in the dimension view. Here we use the green bar to encode the increase after an intervention, and the red bar to encode the decrease after an intervention. We conduct two case studies to evaluate the system. The first case is about the education analysis. Our data includes 3,500 students from a college, and the target is to reduce the dropout rates. The second case is about the marketing analysis. We use a sample dataset with 10,000 visit logs, and the target is to find possible ways of increasing the purchase. Now we will demonstrate the findings in the marketing case. The experts first explore the causal graph and identify a set of expected and certain causalities, like the country as causal effect on the city. This helped them confirm the quality of automatic causality detection. They also found several unexpected and certain causality, like the referral channels influence the number of search. They were excited about these findings and comment that it seems there are far more causalities in the data than I know about. The experts then conduct what-if analysis with the causality. They select purchase as the target and found a set of influential factors, like the login status and the landing page. The experts then try setting the different values of these factors and find possible ways of increasing purchase and obtain multiple plans. They decided to formulate A/B testing to further verify the results and share with their product managers. Overall, the experts approved the usefulness of the causal graph layout, the presentation of the uncertainty, and the usability of the whole system. They also provide suggestions like the dimension view can be improved by adding rich interactions, and the what-if interactions can be strengthened by tracking the history of trials. From the study, we obtained several insights, including keeping humans in the loop of causal analysis can mitigate the pitfalls raised by automatic causality detection, and explaining the causality detection can help users more easily perceive and validate the causality. In the future, we plan to support the causal analysis of temporal variables and incorporate human knowledge into the causal discovery. We thank the founding agencies for their generous support. Thank you for your listening. I'm happy to take any questions.
So thank you, Xiao, for this very interesting talk. Lots of questions on Discord. So the first question from Julian Muller. So the question goes, thanks for the great work. In your title, you also name validation. Which kind of validation do you include in your framework? And are the users able to modify the causal models when identifying possible mistakes?
Thank you for your questions. And so when users find some certain or uncertain causal relations, they can actually input these relations as a prior knowledge to their causal discovery model. And the causal discovery can therefore prevent the mistakes. Yeah. So that's
Great.
the validation.
Okay, and then the next part of the question was, in case of node aggregation, how do you present the edge uncertainty and edge strength?
Well, for the edge uncertainty, we use the thickness of the link to encode. And for the node aggregation, since we only aggregate the chain structure, and in the visualization, we preserve the uncertainty of the head, that is the link that enter the chain structure, and the uncertainty of the end, that's the link that leave the chain structure. And for the link inside the structure, we simply just omit it in the visualization, since at the overview level, we think that users do not care about this really detailed level information. So if they were curious about it, they can expand the chain structure to see the detail.
Thank you for the clarification and your answer. And we have time for just one more question, unfortunately. So for the rest of the questions, you can probably continue that on Discord. So the question is, what are your experiences with the hidden cross layers? Do the users miss these, or have they been fine with your visualization system? I think it is a really nice way to avoid visual clutter. However, you do not present the real structure of the model. And this person is very curious in your own experiences.
Yeah, so according to my experience, the experts actually, they like this kind of encoding, because the hidden layer causes some kind of edge crossing that cannot be easily reduced, and with the so we need to hide it in the overview level. But since we use some very significant, very easy to see some encoding, like the node size, so they can simply see which node has some hidden layer calls. And according to their experience, there may not be so much hidden layer calls, so they're fine with this encoding.
Thank you for the answer. And that ends our session for today. So let's thanks together our presenters. Thank you also to the audience for their questions and lively discussions on Discord. I'd like also to thank our technician for taking care of some glitches during the session. And let's continue the discussion on Discord. So enjoy the rest of this.
We present 3 external labeling concepts that allow a user to browse through point sets without the need of zooming in and out. In the first method, labels are distributed on multiple pages. The next method arranges the labels in a single row that can be continuously slid along the bottom side of the map. In our third method, labels are distributed on stacks, which a user can independently browse through.
In our work, we look at how narratives and gamification can be used to foster development of visualization literacy skills in young children between 11 to 13. We present our own instance of such a game, evaluate it in a between-subject study, and report results. We also detail key design considerations for future visualization-based games and highlight many opportunities for future work.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
We propose V2V, a comprehensive pipeline for variable selection and translation for multivariate time-varying data. Our approach contains feature learning, translation graph construction, and variable selection. To demonstrate the effectiveness of our approach, we compare histogram matching, pixel to pixel, and cycleGAN to evaluate variable translation. In addition, we also compare an information-aware framework to evaluate variable selection.
Hi, my name is Sarah. In my talk, I'm going to be presenting a visualization to display an overview of multiple sequences of events and attributes. The key feature of our visualization is how easy it makes spotting trends and patterns in the data. You can find more info in the links on the right. Thank you.
How to know if a graph is correctly drawn? Are all the aesthetic properties preserved? To answer these questions, we currently use quantitative methods that require graph structure and are computationally expensive. We propose a new method to directly compute these metrics from graph layout images using convolutional neural networks. Below are the results. To know more about our approach, please attend our talk.
What is insight? It is a question that has bothered visualization researchers for a long time. We're wondering whether visualization practitioners think about data insights in the same way as visualization researchers do. So we interviewed 23 visualization practitioners to understand how they think. To find out more about what we found and the implications to the visualization community, take a look at our paper.
The make of continuous color maps. We present the CCC tool, a new web tool for the creation, editing and analyzing of application-specific color maps. For the precise definition of color maps, we developed a new color map specification. This new structure increases the editability by reducing the numbers of colors to a minimum.
MeetQueues is an interactive visual platform which augments existing tools for meetings with features that help people engage and reflect. Its visualization shows if more people are satisfied or uncertain about the contents of a meeting. Attendees can add comments and upvote others' comments. Attendees can reflect on the contents and what happened during the meeting using the summary page sent after it is over.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
Political debates are a rare opportunity for voters to learn valuable information about candidates and their stances on important issues, but they can also be inaccessible for casual, non-expert users. Through a 2-year design study in collaboration with political scientists and journalists, we created a novel task analysis for exploring transcripts as a casual user and developed DebateViz, an interactive tool for visualizing political debates for casual, non-expert users.
We study viscous and gravitational finger-like features in a carbon dioxide storage simulation applied for global warming mitigation in earth science. To support spatial exploration, we extract rich fossils to guide the finger detection. For temporal exploration, we visualize fingers using glyphs and create a tracking graph to identify temporal events.
A short overview of the presentation for a simple pipeline for coherent grid maps. In a grid map, we transform an input map to a tile arrangement. However, current approaches do not perform well on complex maps such as the Netherlands. We propose a pipeline that generates high quality and coherent grid maps even for complex data using a simple pipeline.
This paper explores the efficacy of using narratives as a medium of explaining the causality in causal networks. Now, towards this end, we provide you a glimpse of CauseWorks, a causality visualization system for generating narratives given a set of interventions and objectives for a causal model. And we further validate CauseWorks through interviews with experts. Please read our paper to know more. Thank you.
We propose a method palette-tailor that fully automates the coloring process of categorical data and produces discriminable results. Based on both color and data spaces, our method incorporates 3 scoring functions into a customized simulated annealing algorithm. We apply our method to different types of visualizations and compare it with the state-of-the-art palettes through a controlled user study.
Hi, everyone. It is a work about graph visualization. With one node link diagram, dragging node can change the layout of the diagram as you like. But how about more diagrams? Dragging nodes can be laborious. Please come to our talk about exemplar-based layout fine-tuning for node link diagrams. We will give you our ideas. Hi, everyone. It is a work about graph visualization. With one node link diagram, dragging node can change the layout of the diagram as you like. But how about more diagrams? Dragging nodes can be laborious. Please come to our talk about exemplar-based layout fine-tuning for node link diagrams. We will give you our ideas.
This study presents a method to explore hierarchical data by improving RODViz, one of the visualization techniques for multidimensional data. The user can set options for nodes and check the data in groups or individually in the RODViz. 3 subviews at the right enable the hierarchical clustering structures of selected data and allow the user to grasp the features of selected data. As a result, this system allows more detailed insight into the data while solving the node overlapping problem.
The blood vessel structure on the human placenta can be an important indicator in the detection of birth complications, but the segmentation of the vasculature tree remains a challenging problem. In our work, we show how MRI visualizations in immersive virtual reality can help medical practitioners to identify blood vessels without the need for a contrast agent. We present the results of a user study and lessons we learned for vasculature exploration in VR.
Chiroplasm maps are popular. However, we have better encodings for numeric values. Check out the PRISM map